never pause to think or do your work as needed. Rewind and relearn as needed. I'm going to go fast on purpose so that the video is small enough to post. I'm going to do the green graph in the middle. You should do the blue one on the right. So taking a look, I would build the green one on a sheet of loose leaf, pause and wait till you're ready to go, and I'm going to crank from there, and then you can answer the blue one as you with, either after each problem or at the end. So let's crank this out. What's the starting position? Well, to find the starting position from a position versus time graph, you need to find the y-intercept, right? The y-intercept for any position versus time graph tells us the position when the clock reading is 0. So where the line crosses the y-axis, which is position. So in this case, the starting position is 15 meters. Calculate the average velocity. We know the slope of a position versus time graph is velocity, so you have to take the slope or the rise of a run. To calculate average velocity, we have to do change in position divided by change in time. Sometimes we can just plop in the position, sometimes we have to calculate it. I'll do the expanded version now. To calculate change in position, we do position 2 minus position 1 divided by clock reading 2 minus clock reading 1. Now, in our case, which happened first, at time 0 or at 20 seconds? Well, time 0 happened first, so our second position is going to be based on these coordinates. 20 seconds, comma, 5 meters. We get that from this point and this point. And at 0 seconds, our coordinates up here are 0 seconds, 15 meters. So obviously our second position is the 5 meter mark. So 5 meters is our final position. Our starting position was 15 meters. Our change in time was 20 seconds minus 0 seconds. Now, when we simplify that, 5 minus 15 is negative 10 meters, divided by 20 seconds minus 0 seconds is 20 seconds. 10 divided by 20 is a half, but there's a negative in there, so that's negative 1/2 or negative 0.5 meters per second is the velocity or average velocity for this time. Next up, they want us to write a specific mathematical model. Now, we know that for any graph, if you got a line that's going to follow the format of y equals mx plus b. We replace y with the name of the y-axis or the vertical axis, in this case it's position, where the x-axis is clock reading. So for our specific mathematical model, we replace y with the name of the y-axis. We replace x with the name of the x-axis, that's clock reading. To make it a specific mathematical model, we need to include the specific slope and specific y-intercept. So our slope we just calculated was negative 0.5 meters per second, which represents the velocity, and the specific y-intercept, which was the starting position, was 15 meters. Now, we can put any clock reading into this, and we'll find out some final position, where it would have ended up. So we're going to use the subscript F for final position. This is our specific mathematical model. What the beauty about this is we can find this, we can use this to find the position at any clock reading. So the next question says find the position at 15 seconds. So the 15 seconds goes in for our clock reading, so that's 15 seconds plus our starting position times our velocity of negative 0.5 meters per second will give us the velocity. So according to order of operations, multiplication has to happen before addition. So half of 15 is 7.5, so the negative of that is negative 0.5. A meter per second times seconds. Seconds cancel out, which leave us with just meters. Plus 15 meters is equal to the final position. And just to save space here, I'm going to go ahead and put this over here. 15 minus 7.5 would be a positive 7.5 meters, which is that 7.5 meters, which would be the position at 15 seconds. And if you go up here to the graph, you figure 10 seconds would be halfway through there. That's that. So 15 seconds would be here, and you go up across, and boom, that does seem reasonable, but that would be about 7.5 meters. Next, we're supposed to sketch out a velocity versus time graph. So a quick sketch doesn't have to be scaled or anything. Velocity in meters per second, clock readings in seconds. Our velocity the whole time, the slope was constant. We had a positive constant, or excuse me, a negative constant slope from the position versus time graph. So we're looking at the fact this is a negative constant slope, which had a value of negative 0.5 meters per second the whole time. That was the velocity at time 0, and at 1 second, at 13 seconds, at 20 the whole time. So our slope of our graph, or the line on the graph, is going to be at this value right here has to be negative 0.5, and that's meters per second. And that's going to be a negative constant velocity for the full 20 seconds. Find the area under this graph. So basically they're saying between the time axis and the line we've drawn, so the area under this would be this shape, which is a rectangle. Well, the area of any rectangle is height times base. In this case, the height of our rectangle is the initial velocity. The base is our change in time. Our initial velocity was negative 0.5 meters per second. I forgot my negative sign there. Times 20 seconds. And negative 0.5, or 1/2 of 20, is 10. So that's negative 10 meters, which is the displacement. Now, a reinforcement for that is the fact that if we go back up here and look at how we calculated the velocity, we calculated the displacement for the whole time, which we said was negative 10 meters. So it moved 10 meters in a negative direction. Find the area under the velocity versus time graph. Oops, I just did that here. What does this area represent? And we said that the area under a velocity versus time graph always represents the displacement or change of position, how far it went during that time. What would the displacement be for the first 6 seconds? Well, we just said that the displacement was equal to the starting velocity times the change in time. For this case, our starting velocity was negative 0.5 meters per second, and we want to run that just for 6 seconds. And negative 0.5 times 6, or half of 6, would be 3, so that'd be negative 3. And meters per second times seconds, seconds cancel out, so negative 3 meters would be the displacement for the first 6 seconds. If a fish was swimming 1.6 meters per second, how long would it take for it to travel 48 meters? Well, first thing, I'm going to draw a picture of a fish. There's my fish, and he's got a smiley, happy face, and we'll mark a position of 0. We'll say this is a positive direction. The given information, something is 1.6 meters per second. Meters per second is a rate, and we're going to call that the average velocity, and 48 meters tells us how far it traveled. 48 meters, which in this case we could say is a displacement. They've asked us to sketch out a velocity versus, and what do we have to find? We're supposed to find the change in time. How long does it take to travel? Well, just like in our previous problem, it's helpful to sketch out a velocity versus time graph. In this case, we have a positive velocity of, let's see if I can move that, can't. All right, so we got a positive velocity. I'm going to say that the y-intercept here is 1.6 meters per second, and we don't know how much time passes. We don't know this value over here. However, we do know that the area under this rectangle represents the displacement, which happens to be 48 meters. That's the area under that rectangle. So if we start with the general equation, that the displacement is equal to the average velocity times the change in time. In this case, we know the displacement is 48 meters. We know that the velocity is 1.6 meters per second, and that's times change in time. To find the change in time, which is what we were asked to do, we have to get change in time on the side all by itself. Right now, we're multiplying it by 1.6 meters per second, so to do the opposite to get it by itself. So we'll divide both sides by 1.6 meters per second. It's both sides 1.6 meters per second. On the right side over here, the 1.6 meters per second cancels out, leaving us with just change in time. And 48 divided by 1.6. 48 divided by 1.6 equals 30 are the units. Now check is the value. We have meters divided by meters per second. So looking at these units, we get meters divided by meters per second. That's dividing by a fraction, meters divided by meters per second. That's the same thing as taking meters and multiplying it by the reciprocal of that fraction. So meters per second turned upside down would be seconds per meter, in which case the meters cancel out, leaving us with just seconds, which is convenient because we're trying to find a change in time. So you go ahead and use these as models to solve problems 1 through 8 for the right-hand graph, which I think was blue, and to solve 9B or 9U, if that helps. Good luck.